let's keep going. As per usual, we have a lot to cover today. I want to finish what we were discussing in our last lecture about Fourier PCA very quickly, which is used to extract the independent components or the latent variables of our famous linear model that we have introduced. And then we're going to introduce the most important topic of this class. And no, it's not deep learning. It's something else that's the most important thing. If anything, if you have to take anything out of this class, not this topic, but the next topic is going to be it. So very important topic to be discussed today. So let's go back to ICA, independent components analysis. So remember that we start here with a two-dimensional space or a space of p dimensions in general, and we're given a set of data points as per usual. And actually, let me correct this. It's not very linear. And of course, unknown to us, right? This vectors are drawn from two underlying latent variables, right? One of them is defined by this space here, okay? So let me do this. So let's say this is one latent variable, and this one is the other latent variable, and the basis vectors S1, S2, and then my observations, say, are something like this. And the problem is that we cannot obtain S1 and S2 with PCA as we have been done before. So remember, this E1 is the basis vector, and E2. These two are the two basis vectors of my original space. Now if I am to compute PCA, what PCA is going to do is going to compute the covariance matrix of this. This is the covariance matrix right here, sigma x. But obviously x, my observations here that I have, x1, x2, x3, and so on, is nothing else than a linear combination of my sources, S. And what I'm interested in is S, not x. So what happens is that if I apply PCA, I'm going to rotate this. I can also normalize by the variance, right? So I can whiten the data. So if I apply the PCA rotation and the whitening, then my covariance matrix is going to be a circle. It's going to define the normal distribution with mean 0 and I as identity matrix. Covariance matrix. And then there's two basis vectors that define S1 and S2. Actually, this S1 and S2 that define the latent variables, right, are going to be these ones. Here are my original samples now mapped onto this whitened space given by PCA. And now here, this is the first PC. Let's call it PC1. This is PC2. We've called it before V1 and V2, so they're the same thing. And now what we're left with, it's this rotation. You see this rotation from S1 to PC1. That's a rotation I need to find. Once I find this rotation, then PC1 is going to give me that S1, right? So if I have that angle, let me call this angle here, between these two vectors theta, then this is going to be given by this theta rotation. I can define this rotation in the complex domain, right? So if this is defined in the complex domain, I can define it as e to the power of that rotation, right? So basically, that's the trick that it's being used here. And the final algorithm that we derived in our last lecture looks like this. First, we compute the covariance matrix, which is nothing else than 1 over n, the sum from 1 through n, where n is the number of samples that I have, the number of observations, xi minus mu. Maybe you want to use mu hat to identify that this is the sample mean, not the real mean. Xi minus mu hat transpose. Then you whiten the data, right? So you're going to compute the inverse of this and generate a new set of variables. Let's call it y. And now you're going to compute the weights. Which we defined in our last lecture, which are nothing else than defining this rotation that we are looking for. And this is e to the power of j, the complex number. If you want to use I for complex numbers, that's the same. I just use j not to be confused with that I that I have here in the summation of u transpose yi divided by the sum over OK of Ej u transpose yk. And this is the denominator here, just a normalizing value, okay? Just want to normalize this. Now this u, right? U is taken from SP minus 1, or you could say that I'm taking u from a normal distribution with zero mean and identity matrix. And the reason is that I'm looking for the vector that projects, that gives me that rotation, right? So I'm looking for that u vector here, say this vector here, right? U that gives me that rotation in my space, okay? That allows me to rotate this. And now I can compute mu of u, which is 1 over n wi yi. And, well, it would help if I add the summation, right? Summing wi yi and the new covariance matrix, which is 1 over n, the summing term of wi of yi minus mu u yi minus mu u transpose, right? So now I compute the new mean and the new covariance matrix for that vector u that I'm looking for. And then 5, I'm almost done. I compute the PCA of this new vector u, or this new space, which is nothing else than the PCs of the weighted covariance matrix. So I compute the eigenvectors of sigma u, right? Let's call these capital VU, whose columns are the eigenvectors of sigma u. And now need to return the result. And my result, obviously, for A, right? Remember A, it's the matrix that we're looking for, this matrix right here, okay? This A is nothing else than my solution, the V's that I have selected, let's call V tilde if you will, which are the first eigenvectors that I'm going to select. Or if you want, you can select VU. And I'm going to have to project this back into the original unwhitened space. So I'm going to multiply this by sigma x to project it back onto the original space, right? This is the same trick that you had to do in your first homework or project, rather, to recover the direction, right? Okay. Now, computing the eigenvectors of sigma u is a little bit trickier than computing the eigenvectors of sigma x. So you have to be extra careful when we do that. One solution is to compute the eigenvectors in the complex domain. So you can compute sigma u product and multiply this with sigma u, the complex conjugate of sigma u, and then get the eigenvectors of that. In the paper that I posted in Carmen has additional solution, an additional solution that works supposedly much better than this. So I'll leave it at that. That paper also has an extension or two more extensions. One is the problem with this method generally, as you will see, and that's given by this problem of computing the eigenvectors of sigma u especially, is that you need a relatively large number of observations to solve for u, or for a in our case. And one computation I think that the authors show, they actually show the exact number of samples or the order of samples that you need, but it's usually generally in the problems that we're interested in tens, if not hundreds of thousands of samples in order to solve for this problem, which is generally not ideal. But then they propose a solution for that that can be solved with this new way of computing the eigenvectors. Okay, so interesting reading if you want to dig deeper into this topic. The other limitation that we've been discussing is that for most algorithms, p has to be equal than q. Okay, p the number of dimensions of x, and q the number of dimensions of s, right? So x is defined in the real space, for example, of p dimensions, and s is defined in the real space of q dimensions. And we've been assuming that they are the same, but in many applications in ICA, q is larger than p, okay? And that's problematic. Like, remember the cocktail party problem, we have multiple people talking at the same time, but usually have just one microphone or maybe two. But you're going to have 10 microphones or 20 microphones if 10 or 20 people are talking at the same time. So how do you solve this? Well, the problem with this is that then your observation x, it's a projection of the original space, right? Because the original space, the latent space, it's of more dimensions than the observation, the feature space that you observe. So there is a projection, and then therefore there is a loss. And the only way to solve that problem is by observing multiple observations of different projections of that to recover the original matrix A. That's this projection. Again, I'm not going to go through the details, but the paper does a very nice job at describing the algorithm or an algorithm that can solve for this problem. And in their final method, they're able to compute the latent variables and the matrix, the mixing matrix A, even in the condition where Q is larger than P. It's extremely impressive. Okay, so again, you have the paper in Carmen. It talks about how to do this tensor decomposition. Okay. Yes.
For the second step, for the whitening thing, the yi equals to the sigma x inverse xi, should that be sigma x to the power negative half? Because the covariance of yi will be sigma x inverse instead of identical.
Yeah. So the question is, how do you actually compute these things, right? And I showed here in class how to do the whitening with the PCA transformation. So you first take the eigenvalue decomposition, the eigenvectors matrix, remember? And then you project your sigma x onto this eigenvector space. And then you multiply this by the inverse of -1/2, right, of the eigenvalues. and that will give you the covariance matrix equal to the identity matrix. Okay.
So, is there any feature for the second step?
Right. This is just a generic way of describing this, but I have shown here in class how to do it with an eigenvalue decomposition. Right. There are multiple ways to do these things. There's just one thing or one way to solve this problem. All right. Any other questions? All right, so let's move on to the promised most important topic in this class. And that's Bayes. And we're going to talk about the Bayes classifier, the Bayes error, and some other Bayesian methods. And that's the same Thomas Bayes that you're all familiar with. And we're going to use the Bayes theorem, which is the fundamental result that has been applied to many things, and specifically, in our case, to machine learning. So we're going to talk a lot about this. Now, all this, or most of what we're going to discuss, fits within what's called the supervised pattern classification, or supervised methods. Now, supervised methods generally mean that I have pairs. So when I'm given my samples, xi's, my observations, I also have another variable. Let me call it yi. Right? From 1 through n, I'm still assuming I have n observations. But now not only do I have my feature vector, xi, for example, xi defined in Rp, or maybe the complex domain of p dimensions. And for now, I'm going to assume that yi, it's either 0 or 1, but I'll get back to that. Or actually, you can assume it's either +1 or -1, binary. And this is for binary classification. But in general, I'm going to define a function, h, which I'm going to call the oracle function. Okay. That can tell me what the y value for a given x is. What y represents here is the class, category, or outcome that this observation corresponds to. Okay? So for example, y could correspond as simple as to whether an image that I'm observing corresponds to a specific category, say an apple, or not. Okay? So if it's an apple, I'll generally say y1 is equal to +1. If it's not an apple, I'll say -1. Okay? But it could also represent a continuous variable, in which case it could be, say, the motion or the acceleration of the car, of self-driving car, right? So given an image or a video or a number of sensors that I have in the car, what is the output, the acceleration or the steering, the motion of the steering wheel that I want to apply to the car, the self-driving car, given that observation. Okay? Make sense? All right. Now, in general, we're going to write, as I said, when we do a lot of derivations, that yi it's equal to some function of xi. And remember from the first lecture that I said, in general, machine learning is nothing else than y is equal to f of x, right? So there is a functional mapping between x and y. X my input, y my output, right? And as you can see, everything that we have done thus far falls within that model, right? So f can be defined by the principal components, can be defined by the independent components, can be defined by the correlations, can be defined by a variety of things. We're going to discuss other new things here today, but basically this f, this mapping that I'm looking for, is what I want to approximate. And what do I really want to approximate? I want to approximate to this oracle function that actually gives me the actual mapping, right? This is the true mapping, okay? Now, unfortunately, I don't have h, but I do know the value of xi and yi for a variety of observations, right? So like in your project, we gave you images of apples and cows and cars and what have you, right? And we told you this is an image of an apple, meaning this xi corresponds to the yi equal apple, right? Okay. So that's why this is called supervised pattern classification. You'll also see, as I said, called as supervised approaches or supervised learning. Sometimes you'll say supervised learning. And the reason for that is because this is supervised, right? I am telling you that this xi corresponds to this yi. When I don't have access to the yi, directly at least, then we're going to talk about unsupervised learning or unsupervised pattern classification, because in that case, I don't know why, and I just have to use other mechanisms to make a good guess of what h looks like. Now, the goal today is to see why base is the most important topic or thing that you can ever learn from this course. So let's dig into this. And by base, I mean the base theorem, right? That's all I mean. All right, so let's get us started. Remember that we're talking about, or we are considering that we have probabilistic models, right? What probabilistic models means is that this underlying function h is a distribution, right? It's a distribution that tells me what is the probability of a certain variable of observation x to belong to a specific output y, okay? Right? All right, excellent. So let's start with calling, say, pi, this is a small p, pi of x. This I'm going to define it as a PDF or the distribution of class I. And by class I mean the ith category, the ith class, right? So the apples could be class 1, and oranges could be class 2, and cars could be class 3, and so on. Okay? Now, this is a small pi. Now, capital Pi of x, this is the posterior probability. And one more. Capital Pi, these are my priors. Okay? So capital Pi just define what is the prior probability of observe or having a specific observation for a specific class I. Okay? So for example, if I don't know anything about my world, right? And I give you an image, random image, what's the probability that that image, the prior probability that the image will describe or will show an orange? Well, we don't know. We need to compute this. But in general, it's equally probable than any other object, right? However, if I take a picture of a highway, let's say I go out here to 315, right? And from on top, from a helicopter or a drone, I take a picture of the highway, right? And I tell you, I took that picture at, I don't know, 3 a.m. in the morning, right? What is the probability that picture is going to show a car? That prior probability is very low, right? It's almost 0. But if I tell you that I took the picture at 5 p.m. in the afternoon, what's the probability that the image is going to include a car? 1, right? The prior probability, it's or 0.99999. It's almost 1. It's almost certain that I'm going to see a car in the highway at 5 p.m., right? So that's what prior probabilities represent. The distribution tells me the PDF, remember, is nothing else than a function that tells me what is the probability of observing certain values of x, right? So for a given x, what is the probability that that x is observable? And the posterior is what we're interested in, right? And if I use Bayes' theorem, I can write capital P of x, that's my posterior. It's equal to a small p of x times the prior probability divided by the sum of from 1 to 2, because I'm going to assume here, remember, that I only have, I'll get back to this, 2 classes. So I have the 2-class problem. So I'm going to sum from 1 to 2 pi of x, capital Pi. Okay? This is just a normalizing factor given by the Bayes' theorem. And this is the posterior value that I'm interested in, okay? This one. What do I want to know? I want to know whether the posterior for class 1 is larger than the posterior of class 2 or vice versa, right? That's what I'm interested in. Okay. Now, let's think about this. You see this term down here, the normalizing term? That term is redundant because it's always the same, right? It doesn't matter whether I is equal to class 1 or class 2. This is constant, right? So I'm just going to get rid of it. So I'm going to cancel that. I don't need to compute something that is constant. Okay. Now, I have this left. So what I'm going to write is P1, meaning class 1, right? P1 of x times capital P1 and P2 of x, capital P2, okay? So these are 2 numbers. These are my posteriors without the normalizing term that tell me what is the probability that a given observation x corresponds to class 1 and what is the probability that that same x corresponds to class 2, right? Now, what are you interested in? You're interested in whether one is larger than the other. But let's think about this for a second. What happens if they are equal? What happens if these 2 posterior probabilities are equal? Then which class is more likely? Which class 1 or class 2, is x most likely to belong to? Yeah, go ahead. It's equally probable, right? There's no, that's what the equality means, that x can belong to class 1 and class 2 with equal probability. What does this mean? Let's go back to our feature space. So imagine that this is my feature space of p dimensions, right? And I have certain observations here. These are my xi's or my xj's, not to be confused with the I of classes now. So these are my xj's. Let's say that these are for class 1. And these ones here are for class 2. Okay? So again, these ones here are my xj's, meaning the samples for the first class. And these are, or actually, why don't I say even to make it clearer, I could write x1j, meaning the samples of class 1, okay? For j, we could say 1 through n sub 1, okay? And these ones here are my x2j with j 1 through n2. Right? Make sense? Right? And I could say that n, my total number of samples, has to be n1 plus m2, right? To keep it consistent. All right. Now, what does it mean that the probability is equal on both sides? Well, it means that if I know the distribution of these samples, right? Let's say that the distribution of these samples is this one here, and that these samples is this one right here, then the equality is somewhere here, okay? This is what this equality right here is defining, right? It's defining in a linear or nonlinear, right, line in that two-dimensional space, right? In 3D, it would be a plane, and in more than 3D, it would be a hyperplane, right? And this is called the classification boundary. That means that everything that is on this side of this hyperplane, right, or manifold if it's nonlinear, belongs to class 2. Let me call this region 2 because that region belongs to class 2. And everything that is on this side of the manifold or the hyperplane, I'm going to call it R1 because it corresponds to class 1. You see that? That's what this equality tells me. Now, if this one is larger than this one, then I'm in R1. If this one is larger than this one, then I'm in R2. Right? Okay? Good. So let's derive this a little further. I can rewrite this equality that defines the classification boundary. I can rewrite it as follows. P1, small p1, x divided by small p2, x equals p2, p1. Okay? This is just rewriting the same equation by moving p1 on this side and p2 on this side, right? And now I'm going to take the negative log of that. So I'm going to write that the negative of p1 of x plus the log of p2 of x has to be equal to the log of p1, p2. Okay? So all I've done, I've taken the log on each side, and I've added a negative sign. Okay? That is a super famous equation. It's called the negative of the log likelihood. So this one here is called the likelihood, right? Or the likelihood ratio. For self-explanatory reasons, right? It's a ratio of the likelihood. And this one right here, this famous one here, is called the negative log likelihood ratio. Okay? And you'll see this being used everywhere. All right. And also note that if P1 is equal to P2, that means if the priors of the two classes are identical, which is sometimes true, then this simplifies to the log of P1 of x equals to the log of P2 of x, or P1 of x equals P2 of x, right? Right? All right. So, what's that? The log of P1 of x, a small p, it's equal to the log of P2 of x. Or you could write a small P1 of x equals a small P2 of x, right? Same thing. This is a fantastic algorithm to classify observations. So this is called the Bayes classifier, and it's a classifier. And a classifier in machine learning and pattern recognition is nothing else than an algorithm that, given an observation, it tells you whether it belongs to that class or that other class or that other class, and so on, right? That's a classifier. It classifies observations into categories, okay, or classes. Now, I'm going to say something really bold right now. So this classifier, okay, or this one for non-equal priors, that's the best classifier you can ever design. This is the Bayes optimal, or we're going to call it Bayes optimal classifier. So basically, this is it. That's the end of classification, because that's the best classifier you can ever design. Why do you want to learn any other classifier, right? I mean, we're done. Maybe I'm going to prove you why this is the best classifier I can ever design, and we'll leave it at that, and we'll move on to other topics, because that's it, right? Why do you want to learn about deep learning or anything else? This is it. This is the best classifier you can ever design. Let me prove you that. So imagine that we have this case. We have a two-class problem still. So we have a problem where x, it's just one dimension. So x is in R, okay, just one dimension. And I have the underlying distribution of class 1 is this one. Let's say this one here. And the underlying distribution of class 2 is this one right here. Okay? So far, so good? Everyone? Yeah? Okay. Anyone can tell me with that equation, and I'm going to assume, so again, this is small p2 of x, and this one is a small p1 of x, right? And for simplicity, let's assume the priors are identical, okay? Anyone can tell me where the Bayes classifier is right here? Where they intersect, correct. Why? Because the distribution, the probabilities are identical at that point, right? So the Bayes classifier is defined at that point, x, right, for which p1 of x is equal to p2 of x, right? I'm going to draw it like this. This is my hyperplane, right? Well, in 1D it's just a point, but in more Ds it would be a hyperplane that tells me this is it. This is the Bayes classifier. So I'm going to call this the Bayes classifier. Okay. Now, I'm interested in knowing how much error is that classifier going to give me, right? I'm obviously, no classifier is ever going to be perfect, but how imperfect is it? So let's compute this. It's actually really simple to compute. So I want to compute the probability of the error. Okay? And that is nothing else. And let's look at this. You see this distribution for P1 goes to minus infinity in that direction and plus infinity in this direction, right? But you see after that point in X, all these observations that may be drawn from that distribution are going to be classified as class 2, when in fact they are class 1. We do that because for that X, it's much more probable to observe class 2 than class 1. But obviously, once in a while, I'm going to observe class 1. So this is going to be my error for class 1. And this is nothing else than the area or volume in more dimensions of that distribution, right? So I'm going to write it down right here. I'm going to integrate. How did I call this before? R2 and this one R1, right? So I'm going to integrate over my region R2, capital P1, a small p1 of x, differential of x. And I'm going to do the same for R1. Now for R1, all this area, right, defines the probability of error of having an actual observation of class 2 by classifying it as class 1. It's capital P2, P2 of x, differential of x, right? That's that volume. That's the same as writing, if you prefer. I prefer this form. I like this form better. I integrate throughout the whole space the minimum of P1 of x, or P2 of x. I think that's clear, right? Because at every point, I just take which one is the minimum. Is it this the minimum, or this is the minimum? This is the minimum. So I take this one, right? All right. So now let's prove. It's super easy to prove this. Let's prove that this is the best classifier you can ever hope to design. Okay? Let's design any other classifier. Okay? So obviously this is my classifier right here, but I could have selected another classifier right here, right? Right? This is another classifier. Okay? What happens if I do that? Well, if I do that, then you see this error that I was making here, right? For samples of class 1 not being classified, being classified as class 2, are now correctly classified. So this error disappears, right? Right? That is correct. But now all these samples of class 2 that should have been classified as class 2 but are now classified as class 1 are errors. And what is that error? It is this area right here. Whoa! This is more volume, or area in that case, than I had before. This is a larger error. Okay, no. So we don't want that. All right. Let's go back, because this is not a good choice for us. This is only going to add error. So let's keep this as was. And let's instead move it this way. Okay? We move the classifier in this direction. So now this is no longer an error, but this one is. And this, again, has more area than the previous one. So the error is larger. There's no way for me to move this classifier left or right in my space and get a smaller error than this one. This is called, when you use the Bayes classifier, this error is called the Bayes error. And it's the smallest error that you can ever get for known distributions P1 of x and P2 of x. Yes?
Does that hold for all distributions?
Yes. All right. So that's all I have to say about classification, right? Any objections? Very good. What's the problem with this picture? I don't know what the underlying distribution P1 of x and P2 of x are. I mean, if I did, seriously, that's it. I'm done. But I don't, do I? I don't even know if it's a Gaussian, or, as was mentioned here, is it a Laplacian? Is it super Gaussian, a sub-Gaussian? Is it a mixture of Gaussians, something that we'll see next week? I don't know, right? I have no idea what this underlying distribution is. If I do, though, Bayes, it's the best classifier you can ever hope to design. So Bayes is optimal for, note the wording here, known distributions, right? But that is what machine learning and pattern recognition are all about, estimating that underlying distribution. That's what this course is all about, right? In classification. If I can get a good estimate of my underlying distribution, then I know how to solve the problem. All right. So let's see how we can do that. Now, one thing that I can do, obviously, is I can compute the error and try to approximate my algorithm as close to the Bayes error that I have defined here, which is given by the Bayes classifier, as I can. But there is another problem with this picture that I've drawn here, okay? It's not clear in this one, but let me draw you another one. How about if I draw you now a two-dimensional space? So here, each observation only had one dimension. Well, let's say that this one is defined in two-dimensional space. So x is in the real space of two dimensions, right? So x given by two entries, x1 and x2. Okay. And the two underlying distributions now are going to look something like this. Let's say this is P1 of x. And this one here is P2 of x. Okay? Now, if you want a drawing like this, you can go to the slides or the handouts that you have in Carmen, because you could draw this in 3D. It's just a little hard for me to do it on the board, but you will see something like this, right? Now, you have to draw, say, x1 and x2 like this, right? x1 and x2, right? And now this third dimension, which is the same as this defines the density or the probability, right? So then that distribution that we have here like this, it's going to look in 3D something like this, where this is, of course, three-dimensional, right? You see how this works? It's going to look like a mountain. It's a Gaussian. And the other one is going to look something like this, right? And my drawing skills stop right there. Okay. Now, how are we going to determine the classification boundary for that case? Well, the classification boundary occurs again assuming equal priors, when P1 of x is equal to P2 of x, right? So if you let this grow, right, this one grow and this one grow at the same time, they will intersect some point here, right? And then as you keep growing this, right, this Gaussian, you keep growing it along with this one, you're going to get something like this, right, and something like this, right? So that's going to be your classification boundary where P1 of x equals P2 of x. Okay? What's the difference between this and this? That classification boundary is, it's nonlinear. It's a nonlinear function, right? So now the problem is that I need to integrate a nonlinear function. Whoops. Yeah. So even if I know my underlying distributions, computing the base error is a non-trivial problem, even in that case. So this is how bad things are getting. So you see, went from we solved the problem to I don't even know what the error of my algorithm is, even when I know the underlying distributions in general. I do know for some cases. Let's see in which cases I can compute this. And to do this, let's look at the base classifier a little closer. In particular, I'm going to derive the base classifier for normal distributions. But obviously, the same applies for other distributions that we have already discussed. So this is base with normal distributions. Okay. So now my Pi of x is going to be drawn from a normal distribution with mu I hat to indicate sample mean and sigma I. Sigma I here, you can either write sigma I. If you prefer, you could write sigma x, the covariance matrix sub I, to indicate class I, right? I1 or 2. But for simplicity, I like to just write sigma I, same as I write mu I. Okay? Now, if I input the normal distribution into my classifier, where is it? Up there, right? Then I get 1/2 x minus mu1 transpose sigma 1 inverse x minus mu1 minus 1/2 of x minus mu2 transpose sigma 2 inverse x minus mu2 plus 1/2 the log of sigma 1 over sigma 2. That should be equal to the log of P1 over P2. Okay? So I took the negative log likelihood here, our classifier, right, that defines the classification boundary. And I substitute this for the mean and the covariance matrix, right, the Gaussian distribution. And you know that this is the classical equation we've been working with, right, plus the sigma, the log of the sigma x and the priors. Okay. Now, that equation, this equation here, defines this classification boundary that we have here, right? So this equation defines this classification boundary drawn here, because that's the same negative log likelihood, but with the Gaussian model in it, right? All right, so that defines this classification boundary. As you can see, this equation is quadratic, right? It's a quadratic equation leading to a quadratic classification boundary. However, there is a particular case in which sigma 1 is equal to sigma 2. So let me call this just sigma, OK? Sigma 1 and sigma 2 are the same, so I'm just going to call them sigma. And let's see what happens when I now substitute this equation with sigma instead. So here is sigma, 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 sigma. And then I can simplify everything to mu1 hat minus mu2 hat transpose sigma inverse x plus 1/2 of mu1 hat transpose sigma inverse mu1 and mu2 hat sigma inverse mu2 hat equals the log of P1 over P2. What just happened? That what was a quadratic equation is now a linear equation as a function of x, right? So now our x squared has disappeared from the equation, and all of a sudden I have a linear equation on x. And therefore, in that particular case, when I have a case where these two distributions that I've drawn here have the same covariance matrix, but different means, right? So this sigma and sigma are the same, but obviously this is mu1 and this here is mu2, which are different, right? But in that particular case, this equation is linear, meaning that the classification boundary is going to be a hyperplane. Okay? So this one guarantees that the base classifier is a hyperplane. In that case, computing this and everything else that we're going to compute becomes much, much, much more tractable, right? So we'll spend a tremendous amount of time in this class trying to make the problem linear. All right, this is for the 2-class problem. Let me rewrite this for for more classes when you have multiple classes. Okay, where is my here? So more generally, for more than 2 classes, the C-class problem. You'll see this as C-class classification problem. Some people call it the K-way or C-way classification problem. They're all the same thing. I don't know why, not only machine learning, in science in general, everything that we do comes in different names, just to confuse people, I guess. Like this was not difficult enough. Let's try to make it a little harder. OK, so the multi-class classification problem, or K-way, or C-way, or C-class problem. We are going to define a new function. Let's call it gi of x, which is equal to 1/2 of x minus mu I, transpose sigma I inverse x minus mu hat plus the log of my prior. And note that this is nothing else than what I had here, right? And For classification, I'm going to find the argument I that maximizes my probability, right? That's it. Okay. Now for the case in which the covariance matrices are the same, this is called homoscedastic. Or sometimes you will see it as homocadastic, meaning homo, unique or one, and cadastic means variance, so of the same variance. Okay. So in the homodasticity case, you are going to be able to simplify this, right? In the linear or homoscedastic case, you are going to be able to simplify this to gi of x. It's equal to wi transpose x plus wi. Now, this is wi vector, and this is just a constant, where this wi vector is equal to sigma inverse times mu I. And wi, our constant, is equal to 1/2 mu I hat sigma inverse mu I plus the log of the prior. Okay? So all I did, I rewrote this in a more compact form, right? Where I have sigma inverse mu I that I have here as a vector, wi, and this other term, which is nothing else than a constant, as wi. And anyone can tell me why I did this? Because this defines the norm of the vector and the offset of the, the norm of the plane and the offset of the plane or hyperplane that defines the classification boundary, right? So this is the preferred form that you will see being used. And once we get to, for example, support vector machines or deep learning, we're going to be using this equation all the time, okay? Now, obviously, this is for the two-class case. If you have the k-wave problem, then this is not as neat, but it looks like this. Gi of x, it's equal to x transpose capital wi of times x plus wi transpose x plus wi, where again, this one here is the vector, and this is nothing else than a constant. And now our wi, capital wi, it's equal to negative 1/2 sigma I inverse. Our wi vector is equal to what we had before, but now the sigmas are different, so I'm going to write sigma I inverse mu I. And our constant is, as before, 1/2, actually negative 1/2 should be right. Mu I hat transpose sigma I inverse mu I plus 1/2, actually minus 1/2. Minus 1/2 the log of sigma I. Oh, and I need to add the log of the prior, of course. So this is the more generic form, obviously, this one here. And We might see this once in a while. Some people do use this, but not as often as this one. Okay. We like to work with linear models because they are easy to work with. Once we have nonlinear models like this, it's a quadratic model, but it's still it gets complicated pretty fast. Now remember that when we talk about feature spaces and how to construct feature spaces, we said it's very common to mean normalize, which we keep doing, but it's also common to normalize your feature vectors, meaning that you divide by the norm of the vector, right, of the feature vector, in which case you map all the feature vectors on the surface of a hypersphere, right? That is going to complicate everything, right? Because now all of a sudden our classification boundaries are on the surface of a hypersphere. So for example, computing the base error, even in the case where the covariances are the same, well, not the covariances because the Gaussian doesn't exist on the surface of a hypersphere, but the equivalent distributions of a Gaussian, like the von Neumann or, the Fisher distribution. These distributions, even if they have the same covariance matrix, are not going to allow us to compute the base error. And the reason is that because now I'm integrated on a nonlinear function. Even if my classifier is linear, I'm integrating on a nonlinear surface, which makes it really hard. Now, if I have a nonlinear classification boundary on a nonlinear surface, then forget it, right? It's just like beyond impossible. All right, so in general, I cannot, and I cannot stress this enough, in general, I cannot compute the base error, right? For a given set of distributions, that's what I want to have. I want to compute the base error, but I don't know the underlying distribution of my data, so I need to estimate the underlying distribution. Okay, so we'll find ways to estimate it, right? So as I said, if we assume we use normal distributions like we did here, then what we are saying is, I assume, this is my assumption, I may be wrong, but my assumption is that my observations are drawn from Gaussian distributions, right? Under this assumption, I can compute the classification boundary and the base error. Oops, well, no. In general, I cannot compute the base error because it's a nonlinear classifier, and therefore I don't know how to integrate this. So how on earth am I going to know what the error is? How am I going to give you an estimate of how good any classifier is? Now, the short answer, and that's no joke, the short answer is you can never know. It's impossible. It's impossible, because either you know the base error or you don't, is period. In practice, we're going to use something we're going to call the empirical error. And what's the empirical error? You can call it the sample error, if you will. Remember the sample mean and the sample covariance matrix and the sample everything that we're doing here? That's what machine learning does, right? In artificial intelligence, there are many methods that you could use to design algorithms to make machines more intelligent. Machine learning says, give me data and I'll extract information from that data, right? Yeah, okay, so give me data and I'll estimate what the error might be. Now, is that the best we can do? We'll see. We'll talk a lot about this. As a first introduction to empirical error, we need to define what we even mean by this. And now, this is not as simple as it seems. Let's see why. Okay, as always, we we start with our set of vectors. So let's say capital X, it's equal to a set of n observations, x1 through xn. And I'm going to keep assuming that it's xi, it's given in the real domain of p dimensions. And I have my classifier that I have calculated somehow, which is my function g, right? This is my classifier that I have, like the ones that we've derived here today. And I can then define the true or expected error the true expected error is going to be defined as, let's call it R of some parameters. It's going to be defined in my space of, so we are missing one variable here. We need, since we're in supervised pattern classification, we need also our function h, right? So remember, h is our oracle function. Our oracle function that returns some value y. And I'm going to define this as a vector of q dimensions. So this is p by q that I'm integrating on, right? The p dimensions of the input and the q dimensions of the output. And what do I have? I have gx and some parameters. I'm also, so this is what's given to me by my classifier, right? So my classifier for an x in that space is going to return some classification. And now I want to compare this to my oracle function, h of x, right? How am I going to compare this? I'm going to compare this using yet another function. Let's call it L. And I'm going to differentiate this in my space, the density of x, h of x, okay? Right? This is, of course, the same. I could have written this. This is just another way of saying this is the expected value of L, G, X, hx, right? Right? It's the expected value, nothing else. Now, in some instances, I'm not going to use this, but in some cases, you may actually see it written like this. This is, okay. Omega L omega, comma some parameters, differential of the distribution. And this right here, so this is the posterior distribution, as same as here. This is the Bayesian expected risk, you'll see it called. Okay, but let's not worry too much about this. I just want you to know that this is pretty common. All right, so let's stick with our definition that I've given you down here, the definition of the expected value, okay? All right. Now, again, Pxy is the underlying true probability distribution, right? This one that I have drawn here, right? This one right here. This is the true unknown, obviously, probability distribution function. If I did know that, then I would, and my oracle, then I could compute the true, the true expected error, R. But I need something else to do that, because even if this is given to me, I still need to use this function L. Now, this function L here, it's called the loss function. And the loss function tells me how similar its two entries are. Okay? So L has two elements, A and B, and it tells me how similar A and B are. For example, just as an example, I could say that my loss function is the Euclidean norm, right, of A and B. That is A minus B squared, right? Or the square root of that if you don't want to call it square, right? That's the two norm, okay? Now, if I define my loss function as this, right, as the two norm, that could be called the two norm loss, but I generally call, because this is used in signal processing, this is called the mean square error, right? Or you will usually see it abbreviated as MSE, right? The mean square error. Now, as you may know, if you've taken signal processing, the mean square error can be divided into two components, the first moments of the data, or the error in that case, and the second moments, called the mean and the variance. So this can be written, the MSE of A G of A, let's call it, can be written as the expected value of A minus G of A square, which is equal to the variance, let me put it that way, it's better, the variance of A plus the bias squared of A, right? We will have a lot to say about this decomposition. This is a fundamental decomposition of the error, of the expected error, and therefore of classifiers. Classifiers, the error that any classifier is going to give us can be divided if we use the MSE as a bias and a variance, okay? And for a given error, so if we fix the error at E, I can change the classifier to have more error given by the bias or the variance, and we'll see what that means. Okay? Now, obviously, using the square laws, it's generally called the square laws or the MSE, using the square laws is very attractive, right? Why? Let's think about this. G is our function, our classifier, and I want the output of my classifier to be as close to the oracle function as I can, right? So computing the Euclidean distance between them, right, the two norm between those, makes a lot of sense. But it's the only way I can compute the similarity? Of course not, right? Why do I have to use the two norm? I could use the one norm. Why not, right? So if instead of using the two norm, I want to use the one norm, then that will look something like this. Then our LA is going to be equal to, or A H of A if you want, 1 over n, the sum of A minus H of A, absolute value for all my samples, right? It's going to look something like this. Now let's think about this for a second. What does this look like? This looks like something like this. The two norm, right? If I use the square laws, it's going to look something like this, right? You agree? This is the square laws, x squared. So this is x, and this is x squared, right? Or f, right? The norm that I'm using, okay? But if I use the one norm, it's going to look something like this, right? It's the absolute value, right? Okay. Or maybe let me use, instead of x here, let me use a. because I've been using A here. Okay. Now, when I use the one norm, this loss function is called, anyone? The mean absolute error, or MAE. I could also use the whatever norm, right, that I want to come up with. For example, I could define what's called the log cos h loss, which is defined as LA equals the sum of the logs of the cos h of A minus h of A, again from 1 through n, right? And this one, if I take this, it's almost the same if you plot this. Go home tonight in MATLAB and implement these functions and plot them like this so you see how they behave. Then this error, right, is going to be given to you differently depending on what you use for the norm. The log of the cos h is something between the two norm and the one norm. It's the one norm, but the smoothed out. So it just looks something maybe like this, right? All right, something like this. And so on. And you can say, oh, so this is it. All I need to do is to know which norm I want to use. Obviously, we will see that when we use one norm versus another, we obtain different results. And we'll explain why these different results matter. But in some cases in classification, we don't even want to use one of these norms. In some cases, we want to use what is called the 0-1 loss. Famous loss function. And the 0-1 loss is very simple. And it's used for the two-way classification problems, okay, or the two-class classification problem. And it says, people usually, you'll see it written many times with this 1 like this. You know, like people write the expected value like this. So they'll write this 1, this is the number 1 like this, and then A different than B. And what this really means, this function, okay, of A is that this function is 1 if A is true and 0 otherwise. So what this does is, if A is different than B, meaning in our case, where are we? In our case here, if our estimate given by my classifier is different than the oracle function, then I count 1. I have an error. And my error is 1, period, right? Maximum error. But if they are the same, if they are equal, then my error is 0. I didn't make any mistakes, 0. Right? And that's why this is called the 0-1 loss. I can see it an error or not, period. I don't try to estimate any norm, right? Very useful. We'll talk a lot about this. When we talk about support vector machines, we'll define the hinge loss. And we'll talk more about this when we talk about support vector machines, because this is the loss that is used in support vector machines, which is given by the loss of A. It's the maximum between 0 and 1 minus YA with, again, Y equal H of A. I could have just written H of A here. Okay. This is also used these days quite a bit in deep learning. That's a very common loss in deep learning. There are other losses. When we talk about distributions, we will use the cross entropy loss. I see I'm out of time, so I covered this one and a few other things related to that in our next lecture. And then we still, remember, have to move from the expected error that we're trying to compute here to the empirical error, which is the simple error. Okay? Until next time.